Okay, guys, so we're going to start this conversation by talking about the difference between an ionic compound and a covalent compound. In an ionic compound, remember, we look up the charges and we crisscross, and then we reduce. So, for example, if I have Mg with a 2 plus charge and SO4 with a 2 minus charge, I'm going to take the 2 from magnesium and give it to the SO4, the 2 from SO4 and give it to the magnesium, but then I reduce that down to MgSO4 because 2 can be divided by 2, right? So in ionic compounds, they are already reduced because anytime we write that formula, we always reduce it. And that's because an ionic compound, remember, forms that gigantic ionic crystal lattice where it goes on forever. And so all we're really doing when we calculate or when we write the formula is we're giving the lowest ratio of elements. But with covalent compounds, we never reduce the formula because there can be more than one. With ionics, there's only one way to do it. With covalents, there can be more than one. A really good example of this is the sugars. Most of the sugars are some multiple of C6H12O6 or something very close to that. Okay, like glucose, sucrose, lactose, all those sugars are very similar in chemical formula, and the only difference is how many carbons, how many hydrogens, and how many oxygens. So in a molecule, not an ionic formula unit, but in a molecule, our formula tells the exact number of each atom. And that's essential because there's carbon monoxide, CO, but there's also carbon dioxide, CO2. So that leads us to a very important distinction, which is molecular formulas and empirical formulas. So what you're used to looking at for covalent compounds is what is called the molecular formula. It is a formula that tells the exact number of each type of atom. The trick here, however, is that experimentally, a molecular formula is hard to figure out. If we don't know what the molecular formula is for a compound, let's say I discover a new compound, it is very difficult to use my experiment to just find the molecular formula. What's easier is to be able to find what's called the empirical formula. This is the smallest whole number ratio of atoms in a molecule. And this is usually what we are able to get experimentally. We can usually figure out the empirical formula from our experiment. And we then have to do a mathematical process to get to the molecular formula. So the molecular formula if we reduce it, is going to tell us the empirical formula. And this one is what we can get experimentally. This is the one we want in order to know exactly the structure of our molecule. So an example of that, sorry, I hit the wrong button. An example of that, let's say I had C6H12O6. That is a molecular formula. Okay? If I reduce it, this is a 6 to 12 to 6 ratio. I can divide all of those numbers by 6. Yes, I know, I just wrote 666. Let's not be reading anything into that. So 6 divided by 6 would be 1, so that would leave us with 1 carbon. 12 divided by 6 is 2, so that would be 2 hydrogens. And 6 divided by 6 is 1, so that would be 1 oxygen. So this over here would be my empirical formula. Okay? So an empirical formula is simply the reduced formula of the molecular formula. All right? And the reason we have both is because the experimental is what we can get, or the empirical is what we can get experimentally. The molecular is the actual structure. Okay? So we're going to start by talking about how to get an empirical formula. When we do an experiment, we tend to be able to calculate the percentage. What percent of what I did, what I started with, was hydrogen? What percent was oxygen? And what percent was carbon? Okay? We're going to take those percents Step 1 is you're going to change the percent to grams. And you're literally just going to take the percent symbol off, put grams on. Step 2 is you're going to take your grams and go to moles. And that's going to require the grid. Okay? So you're going to do your give and goes, top left with units, blah, 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 and you're going to go to moles. Step 3 is tricky. You are going to divide all moles by your smallest moles. And that should get you a whole number, or really close to a whole number. And then step 4 is only as needed. What happens, Ms. Cramen, if I don't get a whole number? Let's say you get something like 3.5 or 2.33. Okay, you are going to multiply by a whole number to get whole numbers. And that's very confusing, so I'm going to give you an example. So let's do an example of this. Okay, so we have a compound is 79.8% carbon and 20.2% hydrogen. Find its empirical formula. So step 1 was to take my percentages and change them to grams. So I have 79.8 grams of carbon, and I have 20.2 grams of hydrogen. Step 2 is to go from grams to moles, and I'm going to do that for both of them. So top left matches bottom right, so we're going to go from grams of carbon to moles of carbon. Moles always gets a 1. Grams is going to get the molar mass. So if I look up the molar mass of carbon, it is 12.011. Grams of C cancel, leaving us with moles of C. So we're going to take 79.8 divided by 12.011. So when we put that in our calculator, we get 6.643909749. We're going to go ahead and round that to 3 sig figs. So that's going to be 6.64 moles of carbon. Same thing for the hydrogen. We're going grams to moles. So top left, bottom right, grams of hydrogen down here. We're going to moles of hydrogen. Moles always gets a 1. Grams always gets molar mass. Molar mass of hydrogen is 1.008. So grams of H will cancel, leaving us with moles of H. So 20.2 times 1 divided by 1.008, that's going to get us 20.0 moles of H. And this is kind of the tricky part. We're going to look at the numbers that we just got, and we're going to say which one is the smaller. So between 20.0 and 6.64, 6.64 is definitely the smaller number. So I'm going to divide both of these by that 6.64. That's going to give me 1 for carbon, and then I'm going to do 20 divided by 6.64, and that gets me 3.012048193. Now, because it's 3.0, That's close enough that we can just call it 3. It's not a perfect whole number because this was done experimentally, and experiments are never going to be perfect. So we're not going to get a perfect whole number, but it should be like 3.0 or 3.1 or 2.99. It should be really close to a whole number. So these right here, what I just calculated, that 1 and 3, are the subscripts. So the 1 was from carbon, so the carbon gets a 1. We don't write 1s. Hydrogen gets a 3. So our empirical formula would be CH3. So now that we've done that, let's talk about our molecular formulas. So our molecular formula is going to be a multiple of our empirical formula. So if we know the empirical formula, this is really easy. So to find your molecular formula, you're going to, number 1, calculate molar mass of your empirical formula. Step 2, you're going to divide the molar mass that is given of the molecule by the molar mass of the empirical formula. In the last step, you're going to multiply the empirical formula by that whole number. So when you divide it, it should be a whole number, and then you're going to multiply the empirical formula by that. So let's do an example of this. So we have a white powder is analyzed and found to have the empirical formula P2O5. The compound has a molar mass of 283.9 grams. What is the compound's molecular formula? So our empirical formula is P2O5. And so we're going to start with the molar mass of that. So we're going to take 2 times the mass of phosphorus, which is 30.974, plus 5 times the mass of oxygen, which is 15.999. So the molar mass of our empirical formula is 141.943. So step 2 is to take the molar mass we're given of the molecule, 283.9 grams. Bad Miss Crane. There we go. Divide that by the molar mass of our empirical formula that we just calculated was 141.943 grams. So 283.9 divided by 141.943 gets us 2.000098631. So it should be a whole number. So this is 2. Grams is canceled, so this has no unit. So to get my molecular formula, I'm going to take my empirical formula, P2O5, and I'm going to multiply it by 2. 2 times 2 gives me P4. 2 times 5 gives me O10. So my molecular formula is P4O10. Okay? So those are empirical and molecular formulas. We're going to spend all of tomorrow practicing this. Thanks for watching, guys. Have a great night.